we're going to move. The stuff we've done so far is probably pretty familiar to you, or at least you've heard of. I think some of you were telling me you've been exposed to it. You know, haven't used it in a while, so it was useful. But some of you haven't been exposed to it. But it's pretty basic stuff. It's pretty old stuff. This is really old news. Not much new. And what we're going to move on to now is something fairly new. I did want to address one thing though. I was asked on break about what exactly ARIMA is doing. And I just want to simplify. I'll give you a simple story here. When you're telling ARIMA you have an ARIMA 0, 1, 0, what kind of model is that? First order integration, very good. Right on top of everything, this is great. So ARIMA 0, 1, 0. So no AR, no MA, first order integration. So what are you telling ARIMA to do? What do you do when you have first order integration to take a non-stationary series and make it stationary? Well, not an integrated non-stationary series. The first difference is what just what people differences the key. You're right. And so you're telling me this is telling ARIMA just take the difference. Take YT and subtract out YT minus 1. And then it does a regression on those residuals. Not residuals, on this difference. So when we said ARIMA, comma, ARIMA, the variable, comma, ARIMA 0, 1, 0, we're telling it to just difference it. Okay. And then it does and estimates the constant, right? And it estimates the shocks, right? So that's it. And then you look at those residuals. You don't have to do ARIMA 0, 1, 0, right? You can do that by hand, right? You could just take the difference, right? And just look at the characteristics of the difference. You can look at autocorrelations of the residuals, or you can look at autocorrelations of the difference, right? So basically it's the same thing, right? And so that's what, so you can do it by hand. Now, if you're telling it to do ARIMA, that's easy, right? Because you can do that by hand. You really don't need to do that. But if you're doing an ARIMA 1, 0, 0, what are you asking, telling the stata in this case to do?
To regress the dependent variable on the left.
Well, kind of, yeah. What are you?
Basically taking the residual of YT, regress on YT minus 1. Right.
That's in effect what you're trying to get it to do. What it's doing is it's estimating it from the pattern in the data. If you think about it as errors, what it's doing is it's finding a pattern in the data. It's calculating a row, right? And it's going through an iterative process to find the row. And like we discussed, remember before with Copper and Orcutt, if you notice it goes through iterations when you tell it to go do this. It doesn't just do first, second, third, and then stops, right? Or maybe it takes 5 iterations and then it stops. So it's a Copper and Orcutt approach.
What it's doing is removing the necessity to regress YT on YT minus 1. It's correcting the data to take out that problem. If it didn't do that, you would have to regress YT on YT minus 1. But the result of doing ARIMA 1 is to remove that necessity.
This is basically how it's doing it. Now you can do it in different ways, right? You don't have to use this GLS approach. You could use a maximum likelihood type approach. You can use a Bayesian approach. But this is the first and classic and simplest approach, right? This is basically what it's doing, but without an X. Right? It's calculating. Just looks at the residuals, from basically a regression, and it takes the residuals and produces a row, and then it adjusts the row, the estimate of the row, and then it looks again, and it adjusts the estimate again, and so it's equilibrates to some estimated autocorrelation parameter. And then you take that, what you've done there basically, you're basically subtracting that out, you transform the variable, right? And then you've got a variable which is, if that's the right model, it's purged of the systematic error. All that's left is white noise, right? And how do we tell? We do the ACF, we do the PACF, that kind of thing. And then we could actually do more sophisticated unit root analyses as well, which we're gonna turn to in a little bit. That's basically what it's doing. So you're just telling it to do this kind of thing, telling it a difference, telling it to model an autoregressive process, telling it to model a moving average process. It's that simple. Is that okay? If it's not, you go home, you want more. But that stuff's pretty easy. I mean, we should make sure this is much more important, because this is where I think you need to focus your attention on time series. ARIMA is useful for identifying time series processes. What you want to identify them, because if it's stationary or non-stationary, makes a huge difference, right, in what you can do with it. You don't want to be regressing non-stationary variables on each other, because right, those underlying drift you're going to find in those two series is going to create potentially false, relationships, either understating, completely opposite stating, overstating the relationship between x and y. Okay, so what am I going to suggest you really focus your attention on? I am not, you're seeing vector autoregression up there. I am not Mr. Vector autoregression. There are some people that are going to really push vector autoregression. And the reason why, there is a vector autoregression model, which is a wonderful, wonderful modeling strategy. You've already seen it on the board, called an autoregressive distributed lag. Okay, an ADL, which we'll get to in a moment. That's a form of this. Vector autoregression. You can remember the context. Along comes ARIMA as a response to this limited approach, right? The econometric approach, which is to just take time series error as a nuisance and get rid of it, right? What the ARIMA people are trying to do is actually model it, right? To build it into their actual modeling strategy. And that's useful because it's taking into account dynamics much more clearly. Now, VAR, vector autoregression, came along after ARIMA, some extent overlapping with developments of ARIMA. And it started off as this really, really complicated stuff. It's such a bad acronym too. But it's good that it's a bad acronym, because this was really, really complicated. And so what they did is they simplified it, dropping this moving average process out of it. Basically, the whole point to vector autoregression is right here, is to regress variables. Models a dependent variable as a function of its own lagged values, plural, and lagged values of all other variables in the model. So if you think of it as a y and x model, you've got lag y, second lag y, maybe third lag y, maybe longer lags of y. And then you also have the same number of lags of x. Okay? And the number of lags is to be determined, right? How do you determine that? Mostly you start off and then you experiment, right? You try more or less and you see what you get in terms of both individual level lag, statistical significance, and collective significance, which we're not going to go into today because I'm not going to be encouraging you to use this at all. It's very, very theoretical, right? Because you're sorting, but because it's just lag based on empirical guides entirely. But it's really, really useful. It was useful for forecasting when people were entirely worried about theory. Right? If we can forecast really, really well, then great. We don't know why it forecasts well, but it forecasts well. And endogeneity maybe in forecasting is not a big deal, right? Because it's the future, right? It's kind of hard, right, to see the endogeneity problem. Some people view VAR models as complements to structural modeling, and the nice thing is the VAR model helps us get at this non-stationary time series. This is really why it's one of the real benefits to it. Okay, so basically think of it a bunch of lagged y's and a bunch of lagged x's. Okay, that's the approach. Now, there's one special case of the vector autoregression model, which is this one right here. And here, y times t is a function of yt minus 1 and xt minus 1, right? It's a first order autoregressive distributed lag model. That's what we call it. Autoregressive, remember, distributed lag. Okay? this is a really, really important model. It, along with the error correction model, which we're going to turn to right away, are two general modeling strategies that you want to use when you're modeling time series. Okay. I'm going to introduce you to these. Make sure you understand them. Tomorrow morning, we're actually going to work through a little bit how they can model anything, pretty much, particularly the error correction model, which is well, it kind of assumes this model. But they're mathematically identical, which is cool. Okay. Okay, so just remember this. We've already been introduced to this, and we'll return to this. It's autoregressive because it's self-written, its own variable, regress on a lag value of itself, and then also lag value of your x variable. Okay, vector autoregression was the mother, father, Mark might say illegitimate parents of Granger causality, right? What is Granger causality all about? Well, it was an approach identified by Clive Granger, one of those three big names of time series econometrics in the last 50 years or so, to assess whether or not x causes y or y causes x. Remember we talked about lags being a really useful thing, right? If a lag x causes current y and lag y does not cause current x, well then it makes you think that x is causing y, right? Not the other way around. That was the kind of thinking that led Clive Granger to develop this test of Granger causality. Very, very simple. Null hypothesis, no causality. Given a two variable system, you basically have these four possibilities, right? X does not cause y and y does not cause x. You have nothing going on. This would be something you might find if you have spurious drifting and co-drifting. You might find it. I mean, you may find it with the actual relationship, but it's actually not true. In other cases, you have x causing y, but y does not cause x. Y causes x, but x does not cause y, or x causes y, right? So those are the four options, pretty straightforward. The really neat insight from Granger, though, was that it's probably a big deal, right, obviously. But the really neat insight from Granger is to say, let's go back to this one here. This is a really, really simple sort of Granger. You think of this as a Granger test. What you're trying to say there is controlling for the previous history of y, right? Does x and lag x, right? Not current x. Does lag x add anything? So you've got y, right? It's a historic relationship with itself. And then you've got a measure of x. Does x add anything? Then you do the same thing in reverse. Okay, you've got x on lag x. Does lag y add anything to your prediction of x? A really, really tough test, right? And it makes some good sense. It makes good sense, though, if causality is lag. But do many of you hypothesize lag causality in the way we measure things? If you go to the voting booth, I mean, do you imagine voters going in on, we're going to have a big election in the United States in November, right? Do you think people are going to go in and say, yeah, so what was the economy like last year? How did Obama do in his first 2 years? Think that's what they're going to be asking? No, so it's right off the bat and perfect. You might say, well, causality is by definition lag. Yeah, but how much of a lag? A day? An hour? I mean, people, we typically measure things and we just bury the causal lag right inside our measurement, right? We've got annual data, we've got all kinds of stuff going on in different directions. And so the problem with Granger causality is just that, is we started reifying, if you reify this approach, right, then you start losing the measurement, you start losing the thinking, right? You stop thinking about what exactly is going on. So, no, wait a minute, I don't expect that to show up, the causality. Causality is current in this context, given the way we're measuring things. Or we have to measure things in a way which allows us to use a Granger test meaningfully. And one way you could do that sometimes is when we talked about, you get the natural lags occurring in the data, where you get, you got a measure of this and then along came this. Right? So then you're saying, this happened in January, this came along in February, now you're measuring it in March. Right? Some people will say, well, wait a minute, what about the exogenous effects? Well, but we're going to turn around the causality and do the same thing in reverse. So we're giving both sides an equal shot. So anyway, I don't want to go too far. It's just useful to know if you don't. Granger causality is a lot of people use it. They don't know how to use it like a knife edge test. Oh, we did Granger test. X causes Y, Y does not cause X. Whoa. Whoa, 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 whoa. Just, slow down. Not so fast. Okay. Here's a common type of Granger type. I didn't do a very good job of this notation right here at all. I'm sorry about that. This should be, B1 yt minus 1, B2 yt minus 2, B3 yt minus 3. Then should be B4 xt minus 1, xt minus 2, and then a B6 xt minus 3. But you get the, I don't know what happened here. But basically, there's 3 lags of full X and 3 lags of Y. What we're doing in this case is just saying, okay, we're testing, right, an F test, do an F test, whether the coefficients B4, B5, and B6 should be B6, right? Add anything, right? Whether or not these variables add anything. So basically, are these variables collectively significant? And the way you would do this in Stata is you would run this regression, right? And then you would say test B4, B5, B6, which is saying to Stata, test jointly that this is 0, this is 0, this is 0. And if you reject that, null of no effect, right, well then what Granger would conclude is Granger causality. Right? Not causality, Granger causality. Okay? Important. I probably should have put this in right now. In italics. Granger test requires stationary data. We won't get into why too much. Okay? Save that. Okay, any questions about vector order regression? Basic, just as basic. I mean, of course, there's questions. But I don't want you to understand vector order regression necessarily. I want you to just get a feel for what it is. So basically, lag x's and lag y's. It's a useful modeling strategy if you don't know how x is affecting, something, because you get all these lags, and basically the pattern effect of x on y just could come out. So you get these really nice curves. You don't know. It's an alternative to some extent of a polynomial approach. Okay. Very useful to modeling events like event effect. You can model event effect, which is gradual and temporary, right? With a vector order regression. It just comes out of the data. It comes out of the parameters. Okay. Okay, that's one. Okay, vector order regression. That's one development. Later on, here. Error correction models. I've already talked about some of the advantages of ARIMA, by comparison with this econometric approach. And VAR had some of the same advantages, right? Both are dynamic approaches, whereas the econometric approach was basically static. Okay. Both model they specify. It's up to specify the dynamic structure of the time space. But neither one explicitly model the role of equilibrium or equilibria in the series. And that's where the error correction model came. Now this is an error correction model. Here we have the difference, right? Difference yt, which is yt minus yt minus 1, equals an intercept plus a coefficient on the difference xt. Plus there's this component here. Okay. If you had a non-stationary variable y, right, and non-stationary x, ARIMA would have you do that regression, right? Difference the y, difference the x, and do the regression, right? So what you're saying is the current changes in x lead to current changes in y. The lag changes in x lead to current changes in y, right? That's it. But what if current changes in x are not to y, or not just a function in this case of current changes in x, but they're also sort of a function of the relationship between lag y and lag x. If, let's say, y is too high given the level of x, lag y, what do we expect to happen this time? Given the economy, support for Obama is just too high. What do you predict next time? No change in the economy. 0 change in x. what do you expect to happen to y? It will go down, precisely. And if it's too low, given the level of the economy, you expect it to go up. That's explicitly built in right here. That's precisely what the error correction model is address. So here, long run information, right? Not short run information. Long run information is explicitly modeled. If it's possible, the relationship is not short run at all. It may be possible that the relationship is entirely long run. So you go estimate an ARIMA model, and you find no short run effect. What do you conclude? X does not lead to y. Is it right, correct conclusion? No, wrong conclusion. Right? It's a type 2 error. Right? Most hard scientists will say better than type 1 error, but it's still, most of you trying to get published are going to be thinking type 2 error is more important than type 1 error, right? I mean, the hard scientists are saying, it should be really hard to find anything, right? But people need to find things to publish. So, unfortunately. Okay, so that's really, this is really, really interesting here. This is an interesting kind of model because this is unlike all the other models we've looked at. This has a model that mixes levels and differences, right? Okay, it mixes levels and differences, right? You have differences, and you have levels, right? And then one question comes along, well, what if these level variables, y and x, are non-stationary? What if x and y are integrated? How can we have, right, how can we put these two integrated variables into a model, right? Well, it's interesting that the ECM was actually developed precisely, right, to find a way to incorporate those variables into a model. Not as variables having an effect on each other, right, but on variables, the relationship between which, right, and the errors, right, in the prediction of which cause changes, right, next time. Like we said before, when y is too high given the level of x, we expect a drop in y. When y is too low given the level of x, we expect an increase in y. So what do we expect B2 here? What do we expect the coefficient to be? Positive, negative, or 0?
Correction. Coming back towards something.
Well, we just went through it too, right?
But it was 0.
Well, then there would be no correction at all.
But don't they kind of cancel out?
Well, what if y is 10 and b3 times x t minus 1 is 8? So inside the parentheses it's 2. That means y is 2 units higher than it should be given x of the b3 describes a relationship between b and x over time. So that's basically the regression of the two. You've got there's a 2 higher, so you have the residual from that regression, right? Basically, that's what that is. Yt minus 1 minus the parameter for xt, right, on xt. And then you got the residual, so you get the residual. So it's a residual positive. Well, if it's positive, that means yt is too high. T minus 1 is too high. So what do we expect? T minus 1 to go down, right? Or t, y to go down, then t. So we expect bt2 to be negative, right? Negative times a positive residual. What happens? It goes down. Negative times a negative residual. What happens? It goes up. Error correction. Beautiful model. Beautiful, beautiful model. Because now we can have non-stationary. What's the problem with non-stationary? There are no problems with non-stationary data. Is because what we're modeling is the effect of the difference between these two non-stationary variables, right? Which is fine. If we have the right model relating B and other variables, what are those residuals going to be? Stationary. They're going to be beautiful, right? Now what are we going to be able to do? We're going to be able to model the effect of x, but y as a function of maybe current changes in x, but also the disequilibrium between y and x over time. It's beautiful. Really nice model. So we're going to come back. We're going to work a lot with that tomorrow. And we're going to get to it. We're not done entirely with any of it today. Okay. So related to that is. And this whole discussion of non-stationarity is this unit roots. And to simplify it, some of you will have a more sophisticated understanding of it. Just bear with it because I'm not going to run a full-fledged course, on this unit root, you basically think of this right here. When you have a first order integrated process, you have unit roots. Random walk, unit root, first order integrated process. These are all basically synonyms for each other. Okay. Okay. Right, there it is in a random walk. Parameters 1. Okay, if it's less than 1, then it's a zero order integrated process, right? Because it doesn't have no integration at all. Do something else, right? So in a random walk, if yt is yt minus 1 plus et, well then the difference in yt, right, equals et. So today minus yesterday is just, right, the new shock. Right? The only difference between today and yesterday is the new shock. Which led some really clever economists, econometricians, to say, well, we could come up with this Dickey-Fuller test. Come up with this test where we could say, well, what is the relationship between the difference in y and the lag level of y? If the series is actually integrated, what will be the relationship there? If y is perfectly, if it's a unit root process, so y is yesterday plus the new shock. You regressed the difference between today and yesterday on yesterday. What would the coefficient for yesterday be? Well, we know it's going to be like that, right? So what does the coefficient inside the parentheses have to be? 0, right? And so if gamma is 1, 1 minus 1 will be 0. If it's less than 1, I guess an autoregressive process, right? It's 0.5. This parameter will be less than 0. It will be negative 0.5. So if you have an AR process and you do a unit this test, you'll get a negative coefficient. If it's a unit root process and you do this test, you'll get a 0 coefficient. And so what you're doing here is testing whether this is less than 0. The null hypothesis is 0, right? Right? And that's the question. Okay. So, and this is what a Dickey-Fuller test. These are the classic unit root tests, and you'll see it in Stata we have some really very, very straightforward ways of doing these Dickey-Fuller tests. And what we do is we basically whether or not this coefficient is less than 0. And if it's not less than 0, we conclude, okay, we have a unit root. These are imperfect tests because they're biased towards finding a unit root, right? You have to reject the null of a unit root. Mark is particularly upset about this.
When you fail the test, there's still a 95% chance that you're okay. Right? This is not a nice test.
Well, thankfully, okay, the reason why, okay, thankfully, as you're going to find out, with error correction models, they're very, very forgiving of what you conclude on this test. So whether or not you conclude that a variable is stationary or non-stationary, you can use an error correction model to model the effects, and you're fine. So you don't have to, that's what's great. And so, and this is one of the reasons why Mark is really, really turned on by the error correction model now, because he doesn't have to be so beholden to as a knife edge test biased towards finding unit roots. This is a big test because why do you think they used the null of unit root? Given what we've talked about. I mean, it makes sense. Because if you've got a non-stationary variable and you're regressing on another non-stationary variable, it's a big problem, right? Not a little problem, a big problem. And you don't want to do that. So you got to be really confident you're not doing it, right? So it makes some sense to do it this way. We're approaching it from the point of view of finding truth, not just finding stuff, right? You know, if you want to find stuff, well, then you would do something different, right? But they're actually trying to protect us from making mistakes when they're designing stuff. Right? They're worried about this kind of thing. All right? They're doing battle with the econometricians who want to regress everything on everything else, right? And not worried about it. All right? Okay. Well, those econometricians are pretty much lost, right? Okay, so what do we? Okay, so we're good on time. Okay. There's also something called, I want to mention here, On integrated processes, just so you know, just a little something else. Have you ever heard of fractional? Anybody heard of fractional integration? Just useful just to put in the back of your mind. This is not, there's some people who are big advocates of fractional integration. What some people have shown, good statisticians, including the Eagle and Granger types, have shown if you take a bunch of individuals with different autoregressive processes, say you have a population of people, all of whom have different autoregressive processes, 0.9 or 0.87, 0.72, whatever. When you aggregate across people with different AR processes, you can, not necessarily, you can get a process that looks kind of integrated. Okay. So you know. So mixing of stationary processes across individuals, across shocks, there's all kinds of different ways that you could be combining stationary processes. You can get something that looks pretty integrated, just so you know, since it's back of your mind. That's a little bit of a troubling thing. Keep in mind, in those processes, right, they look integrated even though the fact of the matter is everything decays. This is important not only for an estimation point of view, but remember, if you argue that, if your conclusion is everything ultimately decays, that's a big substantive conclusion too, right? We talked about this with advertising. Does the effect last, or does any of it last, or does it all decay? That's important to know. Okay, so let's go out and continue on with these unit roots. So, okay, unit root diagnosis is important. We saw it in remodeling, right? Why that's important. The neat thing about this unit root test is you can look at the visual, you visualize, right, the data set. You do your ACF, right, kind of, yeah, I think it's a unit root. So then you do your ACF, you get those ACFs, right, those autocorrelations. Then you do your partials, you get that. Now you've got another weapon in your arsenal, right? You can go another test you can do on the data. So it's good, right? So you can do this unit root test and see what you find there. Okay? Also remember we have this non-stationarity regression problem. Okay. What about the error correction model that contains these integrated? What if they contain integrated variables, unit root variables? As I've already said, they enter into this unit root component, which I see this equation down here, so I have it up here again. Probably can't see it. Back. See if I can get it up here. Yeah, well, let's move it out. Okay. They call that component here in parentheses. Okay. This component here is called the error correction component. And so you've got this error correction model with differences in X, right? And then you have this error correction component. And what Granger, Granger who won the Nobel Prize, right? He says pretty good. These two, we have a couple political scientists now, right? Pretty exciting. Eleanor Ostrom and is it Herbert Simon? If the Nobel Prize was given out by American economists, I don't think we'd have that. This is the focus. Granger's Nobel winning insight that the linear combination of two integrated variables would be stationary. This is really, really critical. It's very easy now. It's like, yeah. And when that's true, the variables are said to be co-integrated. And so if you take, what is a linear combination of two variables? If you run OLS regression of y on x, right, you have combined them, but when you generate the residuals, you have basically combined them, right? You have a linear combination. Y is 2x, You take the residuals. They will be stationary. At least that's the theory. And they're said to be co-integrated. And if they're co-integrated, Rangers show that they have an error correction model representation. This is really, we're not going to go through all that. This is a really great finding because now we're able to actually, not only we're able to do these analyses, not worry about the integration, adding non-stationary variables into the model. Not that it was a big world anyway, because we're not regressing them on each other in the beginning. The y is a difference variable, right? But he proved, he gave us the math, and also asymptotics. So how do you assess co-integration? You diagnose integration of y and x, right, here. And then you regress y on x in levels, right? And then you test for a unit root in the residuals, right? So y is integrated, X is integrated, regress the y on the x, we get the residuals, we do that test on the residuals. Are they integrated? Nope. Stationary? Well, then we've got it, right? And then what could we do here? Is we could estimate this error correction model. Right? Again, same model. Where we have the difference in y regressed on the difference in x, and then the residuals from the regression of y on x, right? Lag. You do the regression current, right? Then you just use lag regression. It doesn't make a difference. You will do lag residuals. You can't have the current residuals in there, obviously. And it's not the whole point of error correction. The whole point of error correction is you're looking at the damn last time was too high or too low, given what it should have been. In small, okay, so that's the sort of classic approach to estimating modeling using an ECM when you have integrated variables. It's mathematically equivalent just about to entering y t minus 1 and x t minus 1 separately. Right? If you see right here, there's no reason why you couldn't just write that out as b2 y t minus 1 and estimate that b2, right? And then b2 times b3 x t minus 1, just estimate a coefficient for the t minus 1. Right? You could just estimate this. Right? Instead of estimating the residuals, you could say, okay, let's estimate the difference y, right, regressed on difference in x, and lag y, and lag x. And then you could go mathematically if you want to rewrite this equation as an error correction model with that sort of residual that you would generate. The reason why this is going to be different is that you could have, this was not going to likely be very different if you have big N, if you have long t and long time series. But if you have modest time series, which is what most of us have, the equilibrium between yt minus 1 and x may not be realized in the data really neatly. And so you're better off, in this case, allowing y and x to enter separately. What I always do, I always estimate it both ways. This is called one step, the other one's called two-step. This is called the direct estimation, the other one's a two-step estimation, Granger two-step. I do them both. It's not uncommon when you're dealing with finite, well, really finite, like, you have 25, 30. It's not uncommon for me to find close error correction, close co-integration effects in the two-step. Like right sign, everything's working together, but you're getting a t of like 1.6, 1.7, and you do it this way, and you cross the threshold. You get really nice t's. It's because that other approach is trying to force the effect of x and y to be where it's really not in a short time. Okay. This is not a perfect approach, and I'm happy to go over this. I fully expected to have to go over this. Just to be clear, it is not a perfect approach. You could have concerns about endogeneity here. You could have more than one co-integrating relationship that could be going on, and this has led to these vector error correction models, which I'm not going to voice upon you today. Much more complex mathematically. What do you think? Results? You're smiling. You understand? Do you have any problem with this? Or is it straightforward?
I might have a question which might be stupid. Isn't there
I don't think there are any stupid questions.
linearity between x t minus 1 and delta x?
Can there be?
I think there can, but I don't know.
What if xt minus 1 is integrated? Or x is integrated? It's a good question. What do they say? I really believe, especially in statistical stuff, I think the only best questions are the ones on ask. This is not this. It's not obvious, right? This is not like, oh yeah, I was thinking about that on my own. Yeah. Right. What if xt is integrated? Is there a relationship between lagged x and current changes in x. Well, if it's integrated, what do you expect? Xt. Today's at t. What do you expect x to be at t plus 1? No, not completely constant. But close to constant. What's it going to be? It will be today, but it will also be with something else. A new shock, right? What kind of shock will that be? Stochastic, right? It's totally, unrelated to x. Right. So it could be high, it could be low, and so there should be no relationship at all. That's right. It's a very good question. Now, what if though xt is not integrated?
So then there should be a relationship.
The relationship will depend on where xt is relative to its equilibrium. So the prediction there will be either positive or negative. Or if it's at equilibrium, 0. Question?
I'm just wondering how much is similar to sort of a ceiling effect? Like whether is it possible that the relationship is given because the change cannot be that big anymore because you reach already a level in the x if it's not integrated. So, I mean,
Maybe
no,
What
I
about
don't-
ceiling? Is it related to ceiling effects?
this is what related to.
The whole mechanism we're dealing with, I think.
yeah, I mean the change that you can. So if whether the change depends on the actual size, or whether the change depends on how big the level is, the actual level. I mean, it's what you said, depending on how far it's from the equilibrium. I mean, whether this can end up in a ceiling effect in the sense that if it's very distant, then you can basically hypothesize what sort of correlation is between the change and the size of the effect.
It's a good question. You're getting into the land of nonlinear kind of model, right? And this is fine. You could have a nonlinear model, right?
So it's possible to.
You build it in, just parameterize it. That's all you're saying is that is x, that it's a function of how high or low x and y are to the more faster correction under certain circumstances. This is a very generally neutral, linear characterization. And it makes some sense because it's equilibrium based, right? One possibility, what I'm thinking of, I don't know if you're thinking of this, is if you have two variables that are kind of going up together over time, right? Then you might get to a point where when they get really, really high, you end up with less correction than when they're in the middle. Follow? So like the two variables that are trending over time like this. Do you expect the same error correction all the way across that range? Well, you might say that when it gets up here, a 5-unit difference is not, a 5-unit out of 1,000,000 is a lot less difference than 5-unit out of 1,000, right? So you'd expect maybe more correction here, right? There, 5 just doesn't get corrected very much. But that you can build in.
The other.
But I don't want you to spend too much time thinking about that.
No, I won't. I promise. No,
It's tricky, that's why.
The other question is like it's definitely not for this sort of data or what is normally used. But I mean, if there is some sort of measurement error related to the variables that you're putting in, this model assumes that measurement error is independent from the time point of the observation, right? So, for example,
Well, and measurement error is not related.
yes, that it's
To
independent
the
from
previous
the time point when you take. So, for example, I don't know.
Measurement error today should be unrelated to measurement error yesterday.
Yeah.
Yeah.
Or is there a? I was thinking of, for example, this campaign and stuff, and asking. So if you actually have measurement error on one of the x variables that is correlated with the fact whether you're getting close to an event or not, how would that influence it?
You're getting close to an election.
Yes, exactly. So, for example, it's not measurement. The social desirability effect on some variables that you want to actually get will increase or decrease depending on how close you get to the election, which would mean that the error that is associated with your with the measurement of that indicator is actually related. And I don't think that this correction
Well, it wouldn't be integrated.
Yeah.
It wouldn't be integrated,
So
seriously.
that's
Well, that's one thing. So you're going to have, I mean, it's going to be, yeah, it won't be integrated, right? Because by definition, you're making it non-integrated. Because, I mean, it might be a second order, right? If you difference it twice, you might get it. But I have to think, I'm trying to think about something. I don't have a good intuition for what, like a good example of it. So I'm having a hard time. I mean, when I'm thinking of these things, I usually think about these things in substantive terms. I mean, I'm usually not thinking through the equations. I don't know how you think about statistics, but to me, it's a tool. So it's always, I mean, the great thing about statistics evolves in response to, I mean, it's not the mathematics so much that drives statistical developments, it's the practical need, right, that drives statistical, from the get-go. And sometimes when the mathematics get ahead too much, it just gets ignored, right? People stop paying a lot of attention to it. Because it's as practical enterprise. So, yeah, so you can have, you know, X with autocorrelated measurement error, I guess is what you're talking about, right? Yeah, that would, yeah. Then your diagnosis of the variable would be maybe integrated with an AR process, which you could correct, right? Or some people, I'm guessing, I would try to correct it, but other people might just let it be corrected as part of the error correction model. I mean, one of the things that some people like about the error correction model is that whatever the error is, it's corrected, right, at a particular rate. What you're saying is that it would not show up. What you're suggesting wouldn't show up as error correction, I think, right? It would complicate your estimation of error correction, so you probably need to, you know, first assess the dynamics of the variable. If it's not a straight up integrated process, well, then you can't, you know, and this is going to be a little bit messed up, right? Is that, it's not a definitive answer, but.
Well, no, the answer is definitely says that it's not, so I should correct it, it's not taking care of it in any sense.
Well, it's not explicitly
Yeah.
taken care of, yeah. It depends on, I mean, it would be if it's consistent, or at least reasonably consistent to what you would expect the equilibration, the error correction to be between y and x, but you're suggesting an opposite, I think you're suggesting an opposite process. That instead of y correcting to, I mean, if y is correcting to disequilibria in that or autocorrelated error, then it's fine, right? But it seems like you're suggesting something counter to error correction, that x is changing because of measurement error.
Yes.
And so you don't want to try to have model y correcting to a variable that's modeled with measurement error. But the question is, if that measurement error is it measurement error, or is it the real preference? I mean, what we find, Bob Erickson and I find that people, you know, preferences become a lot more meaningful. Measured preferences become much more meaningful over the course of election campaigns. And so, what we would say is that people's preferences change.
It's more in this sort of social desirability direction, which is not necessarily measurement error. So.
Yeah.
But I mean, the preferences, I mean, or some sort of expression of behavior is not really, so the attitude is not changing, but it's more desirable to stipulate that the attitude is different as you get closer to, I don't know, event or.
Well, in one sense, I think you're raising endogeneity, and this, you know, this is, you know, endogeneity is tricky. I mean, I think any time you can think there's a possibility that y is causing x, and it seems like you're either saying that or there's measurement error. Because I think you call it measurement error, but it sounds like you don't think of it as measurement error.
Well, I don't really have an example of the measurement error would be that. So this was easier to, in the sense of conceptualization. I would assume that there are situations when the measurement error is also linked to that.
But the argument, I don't think you're saying that the change in y is going to be a function of lag x, right? That these changes in x. Although I guess you'd have to think that through.
Yeah.
Well, what do you think of it? If you want to follow up on it, that's fine. Either now or
No,
later.
I need to think it through.
Okay. We could talk. You know, we could talk. Yes.
Just a short remark to what Zoe said. Wouldn't it matter what kind of measurement error it is, whether you have across time and the measurement error is correlated to the other times? So, for example, measurement error at times t is a function twice of t minus 1, and that would be a problem. So if every day the measurement error increases close to some kind of event, but if the measurement error is uncorrelated with the measurement error at t minus 1, then we probably don't have such a problem, no?
Yeah, but I don't understand. I don't know if it is measurement error. It doesn't sound like measurement error increasing, is it?
Well, that's a very unlikely case, I would say,
Yeah.
that the measurement error would be a function of t minus 1.
Well, some people would say it would decrease as you get closer to the election.
Yeah.
Most people would argue that.
People pay more attention.
The preferences, but it's not really, is it measurement error or is it preferences hardening? I would argue it's preferences hardening.
Exactly, yeah.
So, I mean, and there's a lot of evidence for that. I mean, people like party matters more, all that stuff, stuff that you think should matter matters more.
But I think the most important thing here is that this is not a cure-all. This is not a formula that is supposed to give you a perfect cake every time. You know, this deals with the biggest things that have occupied the minds of econometricians. My God, you wish they'd had something more important to do over the last 50 years.
This is pretty
And baking a cake is more important. Anyway, anyway, you know, this deals with a set of really important problems, but it does not deal with everything. And you may find when you have finished and you're estimating some process that it isn't working out. You know, that there is something unexplained that's going on. And that's when you start to think, well, what is it that could be doing this? One of the things that could be doing this is that we're getting closer to the important event. And then you can start thinking of processes that might kick in as you get closer to an important event. Or it might be something about the way measurement is being conducted that is in some way related to this important event. But you don't really think about these things until you start getting screwy results. That's when you and of course, all of these embellishments to the original simplistic econometric approach have been developed because people got screwy results.
Or couldn't model.
Yeah.
I mean, this was really a response to things that we didn't know what to do with. You know, people, I think what happened is typical. People started finding a relationship between these kinds of things, these lag variables and the current differences, but they didn't know why. And then Granger came along and he mathematized it. It was really, really clever. I just want to look. Like, this is. Yeah, statistics is just imperfect, right? I mean, you're trying to figure out how the world works, right? That's what you're trying to do with this stuff, and that's all. I mean, for instance, you know, it might not, you might find, well, if you regress y on x, you find a relationship, and you look at the residuals, and the residuals are not stationary. So what does that tell you? They're not co-integrated. We don't have a co-integration. It means these two variables have this sort of long-run equilibrium together, right? They're integrated together, and so when one goes above the other, one reacts to the other. Both could be reacting to each other, right? They could both be, it could be bidirectional co-integration, right, going on, or error correction going on. But one possibility is you're missing some other x variable, right? You have some other variable. It's not just one. It's not the world's not a bivariate, world, right? I mean, you don't just have univariate causality. You got, maybe there's another x variable you need to have, and then you put that in there. Bam! All of a sudden, now you've got, y on x1 and x2, and then you've got stationary residuals, and then you could go to, so that's, it's just what this is designed to do is to help you see how you can model things. In this case, we deal with two integrated variables, right? Unit variables. Oh my God, what can I do? I'm told you can't integrate. Well, you can model them. It turns out also that the error correction model, this model right here, and here's a nice simple single equation form of it, right? Where you're just modeling y and x directly. In order for you to conclude that there's some kind of error correction, y needs to be integrated, x needs to be integrated, right? You'd like the residuals regressing y on x to be stationary, right? Not integrated. And then you'd like B2, if you find error correction representation, B2 and B3 will both be significant, right? B2 will be negative, right? because that's the error correcting component, right? It does lag value, right? If it's high, it goes down, low, it goes up. And xt minus 1 is providing the equilibrium, right? That's what the V3 does. It puts it on the same metric, right, with the y. That's where the V3 comes from, in effect. Well, the V3, you know, yeah, right, in effect. Plus its effect on y minus 1.
No, quick question.
Yeah.
If x or y, whichever, right, is already integrated, then we need at least three time points.
You need what?
3 measurements in 3 time points.
To do this?
Yeah.
You need a lot more than 3.
Or at least the very minimum would be 3.
You can't estimate 3.
Well, some people, okay, I think where he's going is this: you want to think about the error correction model and the autoregressive distributed lag when we move on to pool analysis, right? Because these models, you know, we could put some i's, right, on all these variables, and we could also put j's, i's and j's and t's, right? We could do all that.
And then you get the n from which you can estimate. But in a classic time series, you can't estimate anything if you've only got 3 points.
But as we'll see, and as you already know intuitively, if you start doing those regressions, here you're doing a regression, say, with 50 time points a second. In one case, right? For one unit. And then you know that time is, you have time dictating your coefficient. If you do that in a pool context, you have 3 time series observations, you lose 1, right? Just by lagging. So now you've got, and now you find, aha, well, we have this relationship between, you know, y and, you know, x. Is it a function of levels across the different units, or is it a function of the 2 time points? Right? Because the coefficients are going to pick up the effect of the levels, right? So if you're high regressed on, high predicts high, low predicts low, right? And all those could be as unit effects, right? There might be no relationship. When for unit 1, y goes high, it comes right back down. Maybe for unit 10, when y goes up, it goes back down. But when you regress yt, right, across these units on yt minus 1, you find a coefficient. Why? Because the levels are all different. So you have to be, that's the conversation we're going to be starting on tomorrow. Any other questions on this? So you need to know ADL. Keep that in mind. There it is. There we are, right? Yt minus 1 on the right-hand side and xt minus 1. Really nice. There's another model which is really, really close to it. It's called, when you're estimating this, we'll see is we'll be incorporating an x sub t. Assuming x sub t is exogenous, which we're going to do tomorrow to estimate this, which we did simplify it. We can do xt minus 1, xt minus 2. But xt and xt minus 1 works a lot better. It's really, we can model all kinds of relationships, including, you know, it gives us exactly what the ECM is here, and then we've got the CCM. Okay. Remember, just like the ADL I just told you about, when you stick in an XT, what do you have? You have, on the right-hand side, you have an XT, you have an XT minus 1, and you have a YT minus 1. All right, so you're able to actually write the one as the other, and I'll show you how to do that tomorrow. It's really simple. What I'd like to do, though, is a little bit of spend a little time with this data. Is everybody clear, though? I mean, I'm happy to answer more questions. Zolt? What's your name in the back of you?
Oh, this will be funny. Zoltan.
Zoltan?
Yes.
Zoltan? Okay. Okay, sorry, it's just, okay. Okay, that's easy. My wife's name's Christina. That's, you know, the C squared. Okay, what we're going to do here is we're going to do some a little practicum. And what I want you to do is it relates to the homework we're going to do tonight. It's really easy. You know, I hope you'll do it. It just doesn't. It shouldn't take you too long. You could do it as a group if you want. You could all get on. You know, if you're going to be going to a bar, one person could pull out a computer and you could do it all collectively. Okay, so you may want to, I mean, for those of you who are not, if you're familiar with data, you know you need to do things like set mem, right? Set your memory in terms of megabytes here, it's 10. What I'm going to do is after class today, just to simplify things, I'm going to send you these slides so you'll have them handy. And I'm going to send you the data set so you have them handy. And I think, Fiona, if you just respond to one of your emails last week, will that go to everybody?
Yeah.
And then some, right?
Yeah.
Okay.
Yeah. Just everyone here. Yeah.
Okay. That's easier than trying to put it online now, right?
Yeah, I can't get it online at the moment. Now that I'm not in the office. Yeah.
Okay.
But I can do it afterwards. Yeah.
Okay. This is mat size. As you probably know, it describes the amount of variables in the size of your matrix, data matrix. And then we're going to use this data session 1, which I think I already have open. Let's see here. Today, let's see what we have here. I know some of you work with R, which is great. Mark is increasingly working with R. I'm starting to use it where I need to. I mean, my approach is if somebody's already written the CAN program for me, I'll just use it. So this data's right there, and I have most of the stuff I need. Some things it doesn't have, so R is useful for that. We actually have to code things. And here, what I have is this next one. Yeah. So we have these variables in here. What I did is I created, we've already looked at some of these variables, I created these 10,000 observations. It's a simulation. And X is the time point, so it goes from 1 to 10,000. It's a big time series, right? But see, one thing about time you have to be real careful of is if you have, let's say you have a process that takes 50 years to manifest itself, right? Equilibrium kind of manifests itself. But if you have observations for a year, I mean, that doesn't do you much good, right? So even if you have monthly data, if you have monthly data, you have 12 observations, right? And if you go to weekly data, you get 52, right? So you've now multiplied your number of cases by more than 4, right? But you don't have any more observation on time. You just have more data points, right? And then you can go get daily data. Now you have 365 data points. But you don't have more time. So there's this little irony too, because you get more statistical significance in pretty much everything you do, because you increase the sample size, right? Even though you don't increase the time over which it takes for these processes to manifest themselves. You have to be really careful. Unlike cross-sectional data, the bigger the n, better, right? Assuming it's reasonably random or representative. Here, in some senses, it's almost worse because it allows you to make inferences, right? More knife edge when you really don't want to. So you do have to be a little careful. So time, it's observations, a number of observations can be really deceiving in a time series. Do you follow me there? You get that point? It's a subtle point, but it's an important point. Observations statistically give you this really give you the ability to discriminate, but you're not able to really, you don't really want that necessarily. Depends on what you're looking at, right? I mean, if you're looking at campaign effects, you might want minute by minute data, right? So you could do like stock market data. You could look at volatility or something like that. Those arch tests, a lot of people, those finance people like to do arch tests. Okay, so what do we create? A bunch of variables. This random number, right, generated again. Normal distribution, mean 0, variance 1. And then a bunch of variables. Q, which is that integrated variable, right, this Q. There's ARA, this is autoregressive, and then ARB, another autoregressive. 0.8, 0.5, there's combined variables, combined autoregressive and cumulative, and moving average, and all kinds of stuff like that, all kinds of variables. Now remember, when you're working with this data set, you need to tell the computer, tell Stata, what's your time variable. And you just do it by time series set x. Okay, if you do that, what it does, you see, for those of you who don't know, it says time variable x, right? 1 to 10,000. 1 unit. Okay, so you want to do that right off the bat. And then when you're working in Stata, time series, There's a number of useful operations here. Lagging, this is L.var, and
It
lag
should also
cycle.
be a small L.
Yeah,
But that looks just like a 1, so it's better to use a big L.
yeah, it's yeah. And then you have lag 2, and you have a difference variable. Remember we difference a lot, right? Differencing, the variable time t minus the variable time t minus 1. And the second difference of differences. You have a seasonal difference if you want to. Won't use that very often, but it's there in case you want it. Now what we typically want to do when we see a variable, right, is what we've already done. This is just useful to go through again. Is this take the variable, it's ts line, q. We've looked at this before. See it wanders, right? You know it's cumulative variable. Is that trend or is that drift? It's actually just drift. What happens is, yeah, this is a hard one, but it looks like trend. That's the problem with drift. Drift can look like trend. We know that this is exactly this, right? I just told you it's yt equals yt minus 1 plus et, so e and t, right? Is normally, it's not just Gauss Markov, it's normal, right? Independently distributed, right? 0, 1. That's exactly how we do it. For it to be trend, what do we need to do? We need to add in here what? Some coefficient b, right? Times time. If you take this variable and you detrend it, so some people might think it's trend, right? It's good for having this conversation. What if you detrend it? What should happen? Let's see. Regress q on time, right? Which is x, right? Predict resid 2, we already have resid 1. Residuals. Okay. If we had, all it is a trending series, right? Let's say it's a trend plus a stationary process added in, what would we find? What should our residuals look like? Yeah, what are we going to try? What are we going to find? What do you think we're going to find? Not good, huh? There's still something else going on there, right? We detrended it. So that's not just a trend, there's something else going on. Well, we think it looks, we did the AC, it looks integrated. Let's just look at the AC Q, right? Yeah, that's pretty serious. PAC Q. Sorry, these emails keep coming through. See anything interesting? Doesn't have the luxury to pay a lot of attention. There we go. That looks pretty. This looks pretty much like an integrated process. How would we model it if we think it's integrated? We want to just we're diagnosing what we want to do. We've done the ACF, we've done the PACF. We can also do a unit root test, right? Dickey-Fuller. Q. Gives you these test statistics. The test statistics for Dickey-Fuller. Remember what the Dickey-Fuller test is? So we've done the autocorrelation, we've done the partial autocorrelation. It looks just like it's an integrated process, right? Be able to draw the conclusion. Well, now we've got this other cool test, remember? And that cool test is, let's take the change, the difference, in Q, and regress it on, TQ, T minus 1, right? And if this is an integrated process, what will that be?
Integrated this time must be the same as last time.
Plus the shock. Plus some random shock. So today's difference difference is unrelated to yesterday's level, right? If it's autoregressive, right, then we expect that to be negative, right? Why? Because when yesterday was high, what do we expect it to go today? Drop. If yesterday's low, we expect it to go up, right? But we know it's integrated, so what should it be? It should be 0, right? There should be no relationship between yesterday and today. All the difference is some random shot, right? With mean 0 and standard deviation, variance 1, right? Just coin flip, day after day coin flip. Not only in terms of direction, but also magnitude, right? So it's just random. So what should we find? We should find that it's less than 0, right? Or not significantly different from 0. Here's the statistics you get from that test, Dickey-Fuller, which is it's just estimating that regression on Q. This is the statistics. Notice here, these are the critical values. They're not your typical t-values because of effectively because it involves a lag-dependent variable. And so they're non-standard. These are called McKinnon values. So they are McKinnon. And here's the test statistic that comes out. And there's the p-values, 0.36. So you're definitely not rejecting it, right? So it looks like a unit root. Just so you know, there's some really neat things you can get out of this. You can get, say, you get the actual regression by typing regress. And there you can see, oh yeah, the lag coefficient is minus 0.0006, which implies the coefficient of lag y. If you regress y and lag y, it looks like 0.99943. That's pretty close to 1, right? Okay, and intercept of 0, basically, right? A little bit. So what do we want to do? There's other things you can do here. Okay, well, maybe we're missing something. Maybe we need to take into account trend. Put in trend. Interesting. Isn't it interesting? That even see how much trend, it looks like trend in that data, doesn't it? Remember that series we looked at? It's the same series, right? It looks like it's negative basically the whole time. It looks like there's trend in the thing. Once you control for the lag level, there's nothing, right? It doesn't trend. It drifts. It doesn't trend, right? Why? What's the difference? Well, one's random. One's a result of random point flips. The other one is a result of systematic effect of time. And that was not the result of systematic effect of time. We can also, well, maybe there's something else going on. We need to check into account. It's called an augmented Dickey-Fuller test. Augmented, added on. And what this does is, you do some lags of the difference. And so here you have cumulative lag 1, right? That's the coefficient of interest. Then you have lag difference in Q, lag second difference, lag third difference, fourth, fifth lag. Still have trend in there. Let's get rid of that trend. Wasted parameter. Doesn't make any difference. Rather, these effects are all, not significant. Nothing going on here. Remember, you have 10,000 cases minus 7 here, so you have 9,993 cases. So pretty good. It's not 15. Right? Okay, so. So what do we conclude? It looks like everything we've looked at, right, tells us it's a unit root integrated process. So what do we do now? If we want just to double check, we could do a REMA. Say I'm a cook, America's Test Kitchen. I hope Susan didn't take note of that after last night's conversation. Okay. A REMA cube. We think it's a what? What process do we think this is? Okay, like the day just hang in there.
Unit root.
What's 100? No integration? We think it's 0, 1, 0, right? Don't we think it's one integration, no autoregression? Remember, autoregression is when you think that coefficient's less than 1. When you think that coefficient is 1, it's integration. So we go 0, 1, 0. Got too many brackets. Good. My eyes are going. Yeah, we did that. Yeah, so what do? We predict the residuals, right? Want to look at that? We remember, all we have to do is, the other way, I'll show you a second. Predict resid, 3, residuals. And then we just do the same thing, right? AC, resid 3. Nothing. BAC, resid 3. Nothing. What do we not do? We could do Dickey-Fuller. Right. Fine. -1. What does that tell us? stationary? What do you think? A t of minus 101. That's usually pretty good. I'd take 3. So that's pretty good. So you may want to log, by the way, if I haven't told you, it's maybe a good time to log. Get a log file open, that's how you do that. Oh, you can have all this stuff handy. I should have done that before, sorry. But here we are, we're always doing TS, we're always setting up TS line, and then we're doing diagnosis, right, as we go along. Okay, so remember this is important, right? Remember, if it's an integrated process, the residuals, once you model the integrated process, in this case you use difference, the residuals will be white noise, right? Which means they'll be unrelated to each other. What do we have here now? So let's do this. We do difference. We'll do Dickey Fuller. Let's see. How do we do this? D Q. Same thing, right? So you can do it arima wise, or you can just do it Dickey Fuller wise. Okay. I want to do some more here. Let's see. Try this. MA and RAAR process. We've already done a little bit of this. Autoregressive and moving average process. Here's the autoregressive process, the phi right over here. And then we have the theta there. That's the moving average process because this is autoregressive times y, 2 minus 1. So that is less than 1. And moving average for this is less than or greater than 0. It's an armhole 1, 1. And again, we do the same thing, autocorrelations, partial autocorrelations. A simple way to do both autocorrelations and partial autocorrelations together is to do a core graph. Okay, I'll do that on this other variable here. Let's do it on ARP. Did I do something wrong here?
You got a dot there.
Thanks. There it is. Core-gram. So what it does here is it gives you autocorrelation here, lag 1, 2, 3, right? So it's what? Autocorrelation of 0.49, then 0.23, then 0.12, then 0.06, decaying pretty much geometrically, right? The partial, basically the same as the autocorrelation, then it goes to 0, right? So what does that look like? Autoregressive with a parameter of about 0.5, right? Here's the Q-test, and can you reject a null with nothing going on? Yeah, definitely you can reject that null. What do we want to do to model this? Just to make sure we've got the right model. Go back to a we could do the unit root test, but do you have any, you're not really thinking of this as being a unit root, are you? Is anybody? With that kind of autocorrelation function, you wouldn't be worried about it too much, right? So in this case, we're going to see it as a 1, autoregressive, 0, integrated, 0 moving average. Model it, right? All right, so what should we have left? Stationary residuals, right? Core-gram. What do we find? No autocorrelation, right? No partial autocorrelation. The Q statistics are all, these are all very, very high. So we don't reject the null, nothing like that. So we just did the ARP. Just did integrated processes, right? And we just did autoregressive processes. Everything I've done, thankfully, is already here in notes. Okay. Any questions on this?
I've got a comment.
Yeah.
I don't really think you should do this all together. I think if you do it all together, most of you will just see it going by on the screen and it will just be small. I think you really do have to do it individually or in twos in order for what you are doing to be absorbed. And at the moment, I'm sure it's just mind, eye spinning. they have this Looney Tunes cartoon where the characters' eyes start going around, and that signifies incomprehension.
I don't see anybody's eyes spinning around.
No, I know, but nevertheless, trust me, there are people whose eyes are spinning, even if you don't see it. But once you have been through this, it'll click. It'll click. You know, it's not that much to do, and as you do it, the things that Chris has talked about will fall into place. It's very logical. It's actually very simple.
It is very simple.
What is difficult is trying to get it all into an afternoon. It's the format that's the problem, not the content. And this homework is designed to extract the content from the format so that you end up the evening saying, oh yes, oh yes, oh yes, instead of saying, my God, my God, my God. And then tomorrow you'll be ready to take the next step. But if you don't do it, and if you don't do it in relatively small groups, this by tomorrow will have been smoke, will have become smoke, and then we'll be trying to build on smoke, and it will give us nothing.
I agree. I mean, obviously, I was just being realistic. The most important thing to learn from today, what to walk away with from today, is this ability to diagnose variables, because it's important to do that. You really can't do much in time series unless you can effectively tell what a variable is as much as you can tell. Sometimes you just can't tell very neatly, right? I'm giving you data where you can tell pretty easily. It's 10,000 cases and the processes I created, right? So I know exactly what the processes look like. What I'm going to do is ask you, I'm going to send you this data set with 3 variables in it, and I'd like you to do diagnostics. So you could come back in tomorrow morning, right when we start, we're going to talk about what the characteristics of the time series, the 3 time series are. You're going to tell me what to do on Stata, and I'll do it. Okay? So you need to do that. In fact, that's. Yeah, I mean, I won't say I won't help you, but I would rather not. You know, I would like to be able to say I will help. I mean, if you were in my class at Temple, that's what I would say. I will go only if so. I will only do what you tell me to. That's what I would tell my class. But you're not my students, so I can't do that. And so but that's what I would like you to do. So that way, if you can't tell me, then, you know, walk out of here not knowing. But I won't do that to you probably. Well, it's important to do that. It's also, you know, as I mentioned, I talked a lot today about the autoregressive distributed lag and the ECM model. Those are going to be the focus of tomorrow. First go through the homework quickly. Then we're going to do ADL and ECMs and show how you can model pretty much any relationship between X and Y that matters to you, that you might find out there. And I think you'll really find it useful. And so in the method, I'll show you how they're mathematically the same. It's really easy to show too. It's not that tricky. It's going to require you to focus. So the first 15, 20 minutes tomorrow morning are going to be easy. Then we're going to work hard, focus, take a break, work hard again, turning to time series cross-section stuff, take a lunch break, come back, and then we're going to cover some more advanced cross-sectional time series stuff, but it's not going to be really, really hard work. I mean, like the morning will be. And then we'll have a practicum to close out tomorrow afternoon. The great thing about doing what Mark said is if you do it, you're going to have me here to talk to in the class and say, why is it not this, and why is it not this, and why wouldn't this work?